Hi, in this video, I'm giving you some brief introduction of the Taylor's and Maclaurin series. Okay, so in the section 9.7, so we talk about the Taylor's polynomial and Maclaurin's polynomial, right? So in the Taylor's polynomial for any function f of x, which is we can approximate the value of a function at x equals to c by using the Taylor's polynomial, right? By using the Taylor's polynomial. That polynomial is given by p and x equals to f at c plus f prime at c times x minus c over 1 factorial plus f double prime at c times x minus c square over 2 factorial plus, and then the nth degree is f to the nth derivative at c times x minus c to the n over n factorial, right? So this is the nth degree or nth order polynomial for that approximate the function f of x around the point x equals to c. Okay, similarly, when you take c equals to 0, then we call that Taylor's polynomial as a Maclaurin's polynomial, okay, of degree n or order n. You see that? The Maclaurin's polynomial of order n has n plus 1 terms, right? You see that f at 0, and then x to the 1 through x to the n is n terms, and then f at 0 is 1 more term, right? Now, so what is the Taylor series then? So the Taylor series is similar to the Taylor's polynomial, but in the polynomials there are n plus 1 terms, right? But in the Taylor series there are infinitely many terms. You see that? You see that all the terms are similar, but there are more terms. So I left just dots, right? That means it keeps going up, okay? But if you write in the series format, how can you write that? Is you can write n equals to 0 to infinity f and c, that is f 0th derivative, that is just f at c, okay? 0th derivative means no derivative, so f at c times x minus c to the 0, that will be 1, so that will be the first term. And when you take n equals to 1, you will get that first derivative term, n equals to second derivative term, and keep going like that, okay? So this is the Taylor series, meaning it is similar to the Taylor's polynomial, but you do not stop on the nth degree, you keep going, okay? That is the Taylor series, and the Maclaurin series is the same as the Taylor series, but we take c equals to 0. So this is the special case of the Taylor series. When you take c equals to 0 on the Taylor series, we get the Maclaurin series, okay? So we will do some examples here, okay? And then after, so I will give you a couple examples how to find out the Taylor series and the Maclaurin series, okay? Let us see first. Find the Taylor series of fx equals to e to the negative 4x at c equals to 0. When c is 0, we call Maclaurin series, right? So this is basically the Maclaurin series. Maclaurin's series, okay, because it says c equals to 0. So how do I do that? Let us find out what is f of x and then f of, because you see that the Taylor series at x equals to c of fx at x equals to c is, you first find out what is f of x. F of x is e to the negative 4x. So you need f at c, right? So f at 0, because c is 0 there, what is that? That will be 1, right? So what is f prime of x? You get negative 4 times e to the negative 4x, right? So f prime at 0 will be negative 4. You see that? What will be f double prime of x then? That will be the derivative of that, right? Negative 4 to the square times e to the negative 4x, right? And if you find out f double prime at 0, c equals to 0, you will get negative 4 to the square. And if you continue that, then you will get f of nth derivative of x will be negative 4 to the n, because how did I know that? Is when there is a second derivative, you have negative 4 to the square. So for the nth derivative, it will be negative 4 to the n, negative e to the negative 4x. And then f of nth derivative at 0 will be negative 4 to the n. That's what you get, negative 4 to the n. That negative sign is inside the parenthesis. Okay, guys. So this is what we get. Now, how do you write down the how do you write down the series format for that is, hence you can write e to the negative 4x can be written as in a series format. Okay, so you can write this is like f of x equals to like that, right? So this can be written as 1 minus, I'm just plugging in here, right? Because f at 0 is 1 minus f prime is negative 4. That's why I'm writing 4. And then x minus 0, because c is 0, right? X minus 0 over 1 factorial is just x, right? And then plus, this is plus, what is the second derivative of f at c? That is negative 4 squared is 16, right? Times x minus 0 squared is x squared over 2 factorial, right? You get 2 factorial. And then plus, okay, f triple prime, that will be triple prime will be negative 4 to the cube, that will be negative 64, right? So you don't need plus there, you will write negative 64, you get x cubed over 3 factorial and then plus so on. But if you write that in the series format, you get negative e to the negative 4x is equals to summation n equals to 0 to infinity, right? And then you write negative 1 to the n times you write 4x to the n over n factorial. How did I get that? You see that the first term is just 1, second term is 4x to the 1, third term is 4x to the square, fourth term is 4x to the cube, and so on. So that's why I was able to write down this is the series representation. Okay, this is the series representation of e to the negative 4x. Okay guys, so let us so this was question number 6 from the book. Okay, now I want to do a couple more examples on that. How do I write down for the series representation of different functions? Okay, so another example is we have fx equals to sine x at c equals to 4. So we have f of x equals to sine x. So what will be f at pi over 4 then? That will be sine pi over 4 is root 2 over 2, right? So find out f prime of x is cosine of x, right? So what will be f prime at pi over 4? That will be again root 2 over 2. You see that? How about the second derivative? Second derivative will be negative sine x, right? So f prime at pi over f double prime at pi over 4 will be negative root 2 over 2. And similarly, what will be the f triple prime, third derivative? Because you see that what I'm getting sine x and then positive cosine x and then negative sine x, and then triple prime will be negative cosine of x, right? And then the derivative at pi over 4 is again negative root 2 over 2. And so let us see one more, because I wanted to see the patterns. Okay, you see that the fourth derivative of x is sine x. You see that it repeats again, so you got sine x again. So the fourth derivative at pi over 4 is equals to root 2 over 2, and then it keeps repeating that sine x and then cosine x and then negative sine x, negative cosine x and sine x and so on. Okay, so how can you write this then? How can you write this as the you see how does the terms look like here? So let us write down that. If you write down this in the series format, so we have, you know that what is the formula? So let me use different color. So f of x is sine x equals to summation n equals to 0 to infinity, right? And then what do you do that? F of n factorial at pi over 4, right? And then you do x minus pi over 4, right? Then, right, to the n, divide by what? N factorial, right? N factorial. So this is the series representation there. Now, but I want to expand this. Okay, so let me write down that thing. Let me move this here. Let me move this, and then let me write down this right here. Okay, so how does that look like? So what is this fn to the pi over 4? You see that at the 0, when n is 0, you got root 2 over 2. When n is 1, first derivative root 2 over 2 again, and then another derivative. So what you can do is basically you get root 2 over 2 for each of the terms, right? Because if you expand that, you will get, when you take n equals to 0, you will get f0, that is the original function, right? You can write, basically you can write equals to, okay, so root 2 over 2 times x minus pi over 4 to the 0 over 0 factorial, that is just root 2 over 2. That is the first term, right? Plus, so when you take n equals to 1, what do you get? First derivative at pi over 4, it is root 2 over 2 times x minus pi over 4 to the 1 over 1 factorial, so it will just stay 1, right? And then what is the next one is the second derivative term, right? You'll get negative sign there, and then negative root 2 over 2, right? Negative root 2 over 2, right, times x minus pi over 4 to the square over 2 factorial, right? And then plus, and then just continue that way. Okay, guys, so here you see that all of the terms have the root 2 over 2 common. Let me take that out, root 2 over 2 common, and then I want to write 1 plus, you see that x minus pi over 4 to the 1, okay, minus, and then you get what, x minus pi over 4. So the first one is plus, right? The second one is square, x minus pi over 4 square over 2 factorial. And if you write down the other term, you will get x minus pi over 4 to the cubed over 3 factorial, and then the next one will be plus, and then like that. You see that? This is what the series representation in the positive, in the plus, I mean in the expanded form. But if you want to write that in the short format, so if you try to write this in the single series format here, okay, because you see that this is a little bit tricky, okay, you should, I had to practice a little bit to write the series format, because the thing is here there is 1, and then another is x minus pi over 4 to the 1, and then there are 2 negative terms, right, and then 2 positive terms, and then 2 negative, 2 positive, like that, okay. So how can I write this? It will look like this, root 2 over 2, okay, and then we can write 1, so 1, and then plus, you can write basically, you can write summation, okay, n equals to 0 to infinity, and then negative 1 to the n times n plus 1 over 2. If you do that, what do you get? If you plug in n equals to 0, you will get 0, right? 0. So negative 1 to the 0 will be positive. The first term will be positive, right? And then let me write down f of n plus 1. That is, what is f of n plus 1? You can write that n plus, let me not use f, because if you use f, you will get the same thing, right? So here, so that can be written as x minus pi over 4 to the n plus 1 divided by n plus 1 factorial. You see that? If you write this way, then if you take n equals to, this is 1, n plus 1, okay? If you take n equals to 0, you will get, this is 0, negative 1 to the 0 will be positive, that's what you get. And then times x minus pi over 4 to the 0 plus 1 will be just 1 over 1, right? If you take n equals to 1, what do you get? Negative 1 to the 1 times 2 over 2 is just 1, that will be negative, okay? Times x minus pi over 4 to the 1 plus 1 will be 2 over 2 factorial, that's what you get. This is factorial there, okay? If you take n equals to 3 though, sorry, n equals to 2, then you will get negative 1 to the 2 times 3 over 2 will be 3. Negative 1 to the 3 will be negative terms. And then x minus pi over 4, 2 plus 1 will be 3. That's what you get over 2 plus 1 factorial. If you take 4, you will get positive. If you take 3, you will get positive. If you take 4, you will get positive. But for 5 and 6, it will be negative, and so on. So this is why you can write, right? Sometimes if you want to write in the single series format at the end, it might be a little bit tricky. Okay, guys, all right, so let us do another example. That is basically example number 14 from the book. Okay, so let me try to do that. So the good thing here is it is at c equals to 0. So what I'm going to do here is I'm trying to find out, let me write down like what is f of x. F of x is natural log of x squared plus 1. If c equals to 0, you get f at 0 will be what? 0, right? That's what you get. Similarly, what is f prime of x? If you find out the derivative of this, you will get 2x over x squared plus 1, right? But f at 0 though is, let me move this color bar on the top. So f prime at 0 is, if you plug in 0, you'll get 0 again, right? Similarly, what is f a double prime of x? It is a quotient rule. If you use the quotient rule, then this is what you get. 2 minus 2x squared divided by x squared plus 1 to the square. That's what you get, okay? And then if you do f double prime at 0, and then you will get 2 if you plug in 0 there, okay? Similarly, f triple prime of x, that is the third derivative. If you do the quotient rule again, you will get 4x x squared minus 3, that's what you get, divide by x squared plus 1 to the cube. And then if you find out the third derivative at 0, you will get 0. You see that? So it looks like the odd derivative at 0, right? And then how about, let me do one more, f IV x. It will be fourth derivative. If you do the quotient rule again, you will get this. 12 is 6x squared minus x to the 4 plus minus 1. Okay, divide by x squared plus 1 to the 4. And if you find out the fourth derivative at 0, you will get negative 12 if you do the fourth derivative at 0. And continue that way, you will get the odd derivative will be 0, and then the even derivative will be after the second derivative, okay? Even derivative, I would say even derivative are basically the non-zero, right? So that's what you get. So if you plug in that into the formula, then what do you get? So the series will look like this, okay? Let me write down the hence natural log of x squared plus 1 is equals to, this is where you get 0 times 0, 0 plus 0 times x, right? And then plus 2x squared over 2 factorial, right? If I just use this formula, right? This is what the formula we are using here, right? And then what is the next one? Next one will be the fourth term, that is the third derivative term will be 0. 0 times x cubed over 3 factorial. And then minus the fourth term will be 12x to the 4 over 4 factorial. And then plus 0 times x to the 5 over 5 factorial, and so on. Okay, and so on. This is the series representation for this series, okay? But if you basically simplify that, just remove the 0 term, what you get is x squared, 2 over 2 factorial is x squared, right? And then minus x 4 over 3. What does that mean? That means that you see that 12 over 4 factorial. X 4 over 2, I think, because 4 factorial is 24, okay? 2. And then the other term will be similarly, okay? And then you will get plus, the another term will be plus. You get x to the 6 over 3, and then so on. Okay, so now if you plug in, because there are some of the terms positive, some of the terms negative, like that. So if you want to write in the single series format, this is what you like: n equals to 0 to infinity, negative 1 to the n. Okay, when you plug in 0, you will get positive. When you plug in 1, you will get negative. So x to the 2n plus 2 divided by n plus 1. This is what you get. Okay, this is the series representation. Okay, guys. All right. So basically in the next video you will see some more application of the Taylor's and Maclaurin series. All right.